Jay Ignath, you're watching Deepak and Jam, and today's topic is time complexity in space complexity. So, this is what I feel the basic foundation of DSA concepts. You should always understand what time complexity and what space complexity your piece of code takes so that you can identify whether it's going to be work on your modern system or not. That is one thing. And we'll more explore on categories of time and space complexity in my further sessions. And uh, you can actually explore how does its time and space complexity looks over the graphs, what is the graphical representation, and all those mathematical, graphical, all those things has been discussed in this video. You can explore each and everything. Right, so let's understand a very important concept called time complexity today. It's not only important, it's very interesting as well. So unless and until you deep dive into what time complexity is and how it is calculated and how it is defined over the graphs, it's very simple, so let's begin with what is time complexity. So in general term, if you understand the definition, so it's very basic definition. It says time taken to run any algorithm. When I say any algorithm, meaning of this is it may be your piece of code. Okay, all right, it must be your piece of code. So what piece of code you write, it depends on us, right? So in our piece of code, there are multiple factors we write a code, right? So when we write a code, we use many things like I use for loops, any loops. It may be while loop, for loops, anything. Okay, while loop or for loop. I may be using recursion, right? I may be using sorting algorithms. I may be using searching algorithms, right? Anything. So there are multiple factors when I write a code. So it's clearly defines and it's clearly mentions that whatever I write, based on these factors, my time complexity would be calculated. Okay, so there is no hard and fast rule or there is no formula to calculate time complexity, but there is always a factors. It depends on your piece of code to understand the time complexity. So let's deep dive. How does it looks like? Let me clear this out. Yeah. So time complexity is always denoted with big O notation. All right. So it is mathematically, you can say it's like mathematically represented as big O notation. And how does the graphs looks like? I'll just explain post end of the session, I would say, because right now let's understand what time complexity is and how it is calculated when I write a piece of code. Okay. So before I start, I would like to mention one thing. I am not sticking to any particular language here. It's not like it's not Java specific or it's not Python specific, nothing like that. Big O notations, mathematically it's like we write big O of something, right? Big O of one. You must have seen like many things as written like big O of n, big O of n square. So we'll understand how those things are written and why it is written. We'll just try to figure out. Okay. So the basic rule we need to learn first. The basic rule in any competitive programming, basic rule is it takes your modern system takes 1 second to execute 10 to the power 8 operations. All right. So this is your, you can call this as formula. This is a basic formula. It is implemented and executed in every modern systems. So on this factor, many things are figured out. This formula is used. It not only used in modern systems, but it actually helps us to optimize our code as well. Okay. So what does it mean? It means like, so whenever you're giving any input to your code, so when you write a code and you give an input, right? So let's say I write a code called I runs from 0 to n. But what is n? How it is defined? N is defined by you, right? You are giving the input to till what it should run. If you are not, then it will run unlimited, right? It's like never ending loop, correct? So deadlock, I would say. So okay, all right. So n is something which we define, right? So it depends clearly like how many operations you wanted to perform. All right. And if it is within 10 to the power 8, if it is less than equal to 10 to the power 8 operations within 1 second, then then your system takes it as yes. If it is greater than 10 to the power 8, it means that you are giving more than 10 to the power 8 operations to run. Then obviously the system fails to execute that. So that's the rule we need to understand before to understand the time complexity. We'll understand how it is calculated now. All right. So let's look into. So I will categorize these things like I'll explain how does every time complexity looks like. Like let's explain first is out big of one. Second one I'll explain big of log n. Okay. And last we'll go with big of and how does this works. Let's see. Okay. So I'll change the marker. So big of one in the sense time taken by the system is very linear here. In the sense it has taken constant time. Okay. So when and how does this has been identified like it is big of one. So for this, I'll write a piece of code. Start from 0 to 10, it says. So what is this? And finally, I'll print, let's say I. Okay. What does it mean? That the loop runs from 0 to 10. So maximum it can run till 10, right? Not more than that. Right? So it is like it can stop at 10. So the constant is 10 here, right? So the time complexity for this will be big of 10, correct? But we know this is constant. And let's say I change the loop to 100 now. Now I'll say that it can run till 100 in the sense 100 is again a constant. We know that there is constant, you understand, right? Constant is something which is, how can I say, like constant, constant. You can say it is predefined, it is fixed. All right. So when it is fixed, we know it stops somewhere. It's not infinity. So infinity and constant are two different things, right? So big of 100. So whenever any loop or any piece of code it runs from 0 to the maximum it can run from constant, some constant number, then you can say it is big of 1 because this, when you put it in graph, this will be a linear graph. When I tell about graph in my end of this session, you will you will actually figure out how things looks like in the graph. Okay. So any constant piece of code will have time complexity big of 1. Okay. So obviously this is 100, 10 are obviously less than 10 to power 8 because we have studied a rule called 1 second is equals to 10 to power 8 operations, right? Not more than that, not less than that is less than that are acceptable, not more than that. Okay. So it is obviously less than or 10, less than or equals to 10 to power 8, then it will be accepted. So whatever things are accepted, I will take it as green flag. Green flag. So this is my concept called green flag and red flag. So we often put into these categories. We put people into these categories, right? We say no, that guy is a green flag, that guy is a red flag, or that girl is a green and red. No offense with girls and boys, but I'm generally telling that how we put people. We see any people who is very toxic to us. We see people who are very, what do you say, irritating to us. Then we say no, that's a red flag. Then I need to maintain my space, right? But in DSA, the same thing applies when less than or equals to 10 to the power 8. It means that you are not irritating your modern system. You are actually smoothly executing a piece of code. So that's why it accepts you as a green flag. All right. All right. Interesting. Makes sense now. Let's go to next called big of log n. Okay. So big of log n is something. I will not write a piece of code for this, but I'll give an example because if I write code now, because you will be quite uh, confused here because I didn't explore the concepts like binary search and other things. But I'll tell you like how generally binary search, or whenever I tell about some topic, then I'll definitely explore a gist of information about it. Although we look more deeply in my upcoming sessions. Okay, so big of log n comes into the picture when you are doing what is log n. Basically, mathematically, if you see mathematically, log n is something when you keep on dividing continuously. Okay, so ignore my handwriting. It's very sweet. It's very good as you have seeing it. But follow my words, guys. Okay. So when you keep on dividing continuously, then we apply log n. So mathematically, that is how the basic definition says. But I don't want to get into more deeply about it. So let's say in binary search, what we do is we simply we have an array. Let's say we have a, as of now, you assume that we have some numbers like 2, 5, 1 and 10. Okay, so I want to search 10, or let's say I want to search 1. Okay, so I can search by going one by one. That's called linear search. That will take more time. So there is a concept called binary search where we do one thing, where we divide these two arrays into two equal parts. It's my first part, this is my second part. Then again, before dividing we sort this array. Okay, so let's say I do like, right. So let's look into this big of log n concept. So here I may write piece of code of counting of factors. Okay, sorry, I'll change my marker. It's very confusing again. Let's say I'll take this. Let's say I'll write a code for counting of factors. Okay, but not the whole code. Just I'll just write a glitch like how do you count a factor. So let's say I've given my number as 10. What are my factors here? Tell me. What are the factors of 10? 1, 2, 5, and 10. Correct. So to get all these numbers, I need to explore from 0 to 10, right? Not 0 to 10, but 1 to 10. My range should be from 1 to 10, right? I need to check each number, like 1 is my factor or not, 2 is my factor or not, 3 is my factor or not. Keeps on till 10 is my factor or not, right? So these all things to explore, I need to go one by one linearly, correct? But if I can apply something like, we know that 1 is my factor and 10 is my factor, right? It means that I, let's say I is 1, okay? So n by I is what? N is nothing but my last number. Like n is 10, right? So what is 10 by I? 10 by 1, correct? So 1 is my factor and n by I. N by I is what? 10 by 1 is 10 again. 10 is also my factor. You see the second one. When I equals to 2, what is n by I? 10 by 2, which is what? 5. So 2 and 5 are my factors or not here, correct? So whenever I is factor, then I can say my n by I is also the factor, correct? So I and n by I are my factors. So whenever I write like this something, I less than equals to n by I, then if I simplify this, it says I square less than equals to n, correct? So I am actually reducing the number of iterations, right? I am not exploring one by one. Now I'm doing, I can go with square. I can go with now I don't need to go one by one and check. I can check like if if one is my factor, then 10 can also be my factor, right? So I will somewhere I check like my 1 square is less than equal to n or not, 2 square is less than equal to n or not. Similar way I can go. So here I am reducing the number of steps, right? Okay, so somehow you will understand when I tell you the count of factors code. But right now, just try to understand that I am reducing the number of factors by 2, right? So there you can apply like big O of log n of time complexity. So again, this law, when log n in the sense what? If n is 10, then log 10 is what? It is less than, right? Less than n, correct? Definitely, this is also going to be my green flag because it is again less than or equals to 10 to the power 8. So this also can be called as my green flag. Okay. So now what is the last one is big O of n. For this, the code is very simple. I'll use a for loop and I'll write from 0 to n. N can be anything. N can be like, not infinity definitely, but n can be maximum till what? N can be 10 to the power 8, correct? Not more than this. If it is going more than this, then I cannot be treated it as green flag, right? So in that case, it will be a red flag. Okay, but right now we are actually talking about green flags, so let's talk positive. So whenever this piece of code executes, then this can be categorized as we go of n as time complexity because your piece of code running from 0 to n, maximum till, in worst case, maximum till 10 to the power 8. Okay, in other cases you can run till 100,000 lakhs crores, but in worst case you will run till the last, like 10 to the power 8 is your last, you will run till that. So always you have to assume the worst case scenarios. Okay, so I'm running my code till 10 to the power 8, then my order big of n will be my time complexity. So this is also less than equal to 10 to the power 8, right? It is equal to 10 to the power 8 now. It can be less than, but I'm taking equal to 10 to the power 8, right? This also can be treated as green flag. Okay, right. Right. So we look into the next one now. It's called something we have called big of n square as well, quadratic equations. The next one we have big of n cube as well, uh, cubic equation, and finally a big of uh, to the power n. Okay. So something like this. We have time complexity like this. You can see. I mean, you will obviously see some piece of code that will represent this time complexity as well. That's what I wanted to say. So when this comes into the picture, we'll see like why quadratic equation comes into the picture. Let's say I use a for loop. Okay, I'll use a for loop that says I runs from 0 to n. All right, and I'll run a one more loop called j also run from 0 to n. In this case, what happens? So we'll try to understand. Let's say I equals to 0. When I equals to 0, j will run from 0 to n, right? Correct? In this piece of code. When I equals 0, j will run 0 to n. What about when I equals to 1? Again, j will run from 0 to n, correct? Because every time you are picking one element, at that moment you are also running from 0 to n, right? So for every integer of I, the j will run from 0 to n, right? So you are running from I from where to where? 0 to n again. So you will run I also you will run from till 0 to n, and for every n, for every I you are also running j at 0 to n. So it also will be n. So it will be like n into n, right? So that's the reason it is like big of n square. So you will see this kind of code written when you are iterating through arrays or 2D arrays. That will come into picture, but not now. Okay. So and how does this affect? How does this affect? Any clue? Because we know our powerful rule 1 second is equal to 10 to power 8 operations, correct? So it can go till what? 10 to power 8 operations only. Now your n is going to 10 to power 8 and one more n, j value n also going to 10 to power 8. So now it is like 10 to power 8 into 10 to power 8, which is 10 to power 16. 10 to power 16 is greater than or equal to 10 to power 8, right? That breaks a rule. So this is now a called red flag. This piece of code you cannot take to your system because it's a red flag. It cannot go. Okay, so do not say it's red flag or green flag in your interview. Just to make you understand, I just introduced this concept because it's more of relating to real life. So that's the reason. So make a habit of sticking to this platform with this concept, not to go out and tell about what is green and what is red. And then if you say this to if you say this to your interviewer, then he's like, what? I mean, he never explored this, right? Red and green. So this is my concept, guys. So do not leak it out. Right. So we'll check the next one. Big of n cube. So in this case also we'll see like the same thing. All right. So I'll change my cursor. Same. I'll use one for loop I from 0 to n again. Let's say I'm running I from 0 to n. In the same time, next moment I'm running j. For every I I'm running j. That also running from 0 to n. The next moment, let's say I'm using one more for loop called k. That also running from 0 to n. So here what happening is for every I, j is running to 0 to n. Okay. And for every j, k is running from 0 to n. Okay. For every I, j is running 0 to n. For every j, k is also running from 0 to n. So it means that it is like n into n into n times, right? For every iteration, it is running like n into n into n. So it is cubic equation n cube. So how does it breaks a rule? It's very simple again, right? How it breaks a rule, we'll understand this. Like you can understand like I is running from 10 to power 8 till 10 to power 8. J is also running till 10 to power 8. K is also running till 10 to power 8, correct? So it is like 10 to power 8 into 10 to power 8 into 10 to power 8. Understood? Like 10 to power 8 3 the 24. So it is greater than or equal to 10 to power 8, which is again breaking your rule. So this also can be called as red flag. So these are the piece of code you should aware of and you should never take to your system. Okay. So understand this big of 2 to power n. I need some extra spaces, so I deleted all those. I'll take an example of Fibonacci series. You know what is Fibonacci series is? Fibonacci series is something looks like something like this. It keeps on summing of the current element then the previous element. Like it's let's say I start with 0 and 1 are the two primary element it starts with. Then it says 0 plus 1 is what? 1. 1 now 1 has come. 1 is my current element. This is my previous element. Current plus previous again 2. Now this is my current element. This becomes previous. 2 plus 1 is 3. It keeps on going. 3 plus 2 is 5. 5 plus 3 is 8 and keeps on going. Okay. So this I need to print. I will write a Fibonacci series code in let's say recursion way. No, let's say something I write like Fibonacci, okay, of n. I'll accept some number. Like let's say I have given like how many till what length I need to print my Fibonacci series will come into this n. Okay. So obviously, if it checks a base condition, it says if n is less than equals to 1, it means like if it is 0 or 1, then I need to return 0 and 1 only, right? I'll just give return n. Ignore this logic of code because you need to understand why it is like 2 to the power n. Okay, I'll this when it comes into picture we'll go deep dive and think about these things, but right now just I'm just writing the code so that you get how things work. So or else I'll just return Fibonacci of I'm calling this same method again. So this is called recursion, calling your same method again and again. I'll say n minus 1, okay, and plus Fibonacci of n minus 2. Okay, so what happens here is if I tell you like so first I'll call Fibonacci of, let's say I choose something called 5. Okay, next it will be coming as here, and 5 is not less than equals to 1, right? This base condition it will be checking. No, then it will return this 2. What it will return? It will return Fibonacci of 5 minus 1, 4. Okay, and Fibonacci of, one second, it's a plus Fibonacci of 5 minus 2, what is 3, right? Again this will be splitting to Fibonacci of 4 minus 1, 3, plus Fibonacci of 4 minus 2, alright. This is splitting to these two again, right? Similarly this will be splitting to again Fibonacci of 3 minus 1 is 2 and Fibonacci of 3 minus 2 is 1, right? You can see the difference, see this pattern guys. Okay, so I'm not exploring more again, this will be very lengthy. So here it is like only one element was there, here it is like two elements, two times, and here 2 becomes 4, similarly it will become 8, correct? So here it is like pattern is 2 to the power 0, 2 to the power 1, 2 to the power 2, because 2 to the power 0 is 1, 2 to the power is 1 is 2, 2 to the power 2 to the power 2 is 4. Similarly, it keeps on growing exponentially. Alright. So that's the reason this time complexity would be big of 2 to the power n. So this is how you identify the pattern and you are deciding, because whatever, as I mentioned, whatever you are writing your piece of code on that factor, it will be decided what time complexity it is holding. Okay. So there is no big deal in this. Okay. So one thing that if you've observed from last past minutes, whatever we have learned till now, there is a order of time complexities, like what is greater and what is smaller, and how we got to know, right? Or how we explored every time complexity, and we got to know how does whether it's a green or red flag, right? So we know that green flags will always stay on priority on top because it is accepted by the system, and this should be the rule, right? Green flag should be less than equals to red flag. Green flag time complexities will be less than equal to red flag time complexities. Let's look the order now. Okay. Initially we started with what? I'll change my marker to this or something. This is very special here. Big O of 1 was what I started. We observed this is less than what? Big O of log n. Correct guys? Right? Big O of log n is less than big O of, sorry, big O of n. Right? Big O of n. And we observed that uh, big O of n is smaller than big O of n square quadratic, and this is smaller than big O of n cube cubic equation, and this is smaller than big O of 2 to the power n, and some more we have called big O of n factorial as well. This we didn't see, but probably we'll see in our next sessions to make this, because everything, if we go detailedly, then this video would be very longer and things would get boring. Okay. This is the order guys, so you know that this time space, what do you say, like the time complexity with constant will be always smaller, then comes log n, then n square, and so on. This is the order you should always remember. This is the optimization order, you can say. You keep on like you may write your code and you get your time, time complexity as this, but interviewer will ask, can we go little lower and reduce your time complexity to this or this or this? Okay, so you may write your code and your code may standpoint at some random time complexity. The interviewer will always ask to reduce it. If you are writing a optimized code already, then you are all set, then you are like pro on this. Okay, next thing is graphs. In graphically, how mathematically it is represented on graphs. Okay, it's like let's look, it's very simple one. No need to go detailing, just a small information we need to know how graphs looks like in based on time complexity. Okay, so the first is what, big of 1, right? So it is linear. Always remember, the linear graph will be linear like this. Linear what? In the linear in the straight line, right? This is big of 1. Okay, now the second one is what? What is the next order? Big O of log n, right? We'll go with this. Big O of log n, something goes like something goes above this. This is linear. This doesn't match the curve. Okay, this is not a curve, right? This is a linear. And this is a little curve graph, big O of log n, right? And if I say little linear like this is big O of n, correct? Now the graph, what the next graph takes like this, called big O of n square, because quadratic, and something like this called big O of n cube, right? Something like that, and more curving opportunity it takes like this, called big O of 2 to power n, and finally it's like this, called big O of n factorial. This is how graphically it looks like. Okay, so you must have understood now how graphs works, and how time complexity is calculated and how it looks like, and what are red flags and what are green flags, and how do you put those time complexity in your red and green category. It's up to the formula, right? And let's revise the last basic formula is 1 second is equal to 10 to the power 8 operation. This should be printed in your mind, guys. Very important to understand. Okay,